The climate, the word we should associate with that, one of them is dynamic. It's changing, and we think of it in terms of a human lifetime, and in a human lifetime it is relatively stable or static. But it's a mistake. It has been dynamic. A number of reasons for that. Some of them are natural, some of them are associated with human activity, as we all know. And there's overwhelming evidence to suggest that the humans are, if not the major, certainly one of the major factors in looking at some of the trends I'm going to describe to you. I'm going to talk about some historical trends, what we do know from the instrumental record. I want to say something about climate variability and extreme events, and then we'll end with some projections of the future. And if we were to do the 10-cent version of what I'm going to say, one of them is warmer and wetter. And I'm going to go through a number of different pieces of data. And again, it's evidence. It's the best science, the best data, the best observations that we have, but together they tell a story. I'm going to start with a historical record for the Earth itself, globally. This is not an easy thing to do. We have measurements in some parts of the world and parts of Europe that go beyond 200 years with advent. Of course, the thermometer's not been around forever. Rain gauges go back much further than that, but an attempt by people to try and begin to monitor the environmental conditions wherever they may be. But it's pretty rough. It's little pieces of it, and in general, most of the science where we have some confidence about what actually is happening begins in the middle of the 19th century. This particular series is shortened a little bit. Warning ahead, you're going to see many of these time series graphics. We're going to be looking at changes in different variables over time. This is global temperature. All the observations that they're actually quality controlled. And each one of these bars here is a difference between the average temperature that year based on the data and a long-term mean temperature. It happens that the period that was used was 1901 through 2000. So if you've got a negative value here, these are in degrees Celsius, you have a year that was cooler than that long-term mean, and the reds, or positive numbers, of course, are opposite, where that year was warmer. And what you can clearly see here is that globally, that the world has been warming up. And there, again, this really is not debatable. I think maybe 20 years ago, 25 years ago, there was still some uncertainty about this because of the technological changes. There's a number, but those things have been ironed out, and all of the evidence points to a warming world. You can see that's true also in Michigan. 2016 is the record warmest year, and it had to do with the El Nino, so the oscillations of ocean temperatures. But you can see here that also the last 5 years have all been the warmest years on record. 2018 probably is going to be the fourth warmest year on record, but there's just an unmistakable upward trend here, especially over the last half century. Again, the world is getting warmer, ice is melting. There are a number of other pieces of evidence that are associated with this. This is just an unmistakable trend. Let's go to Michigan. Let's go closer to home here. What you can see in Michigan, each of these individual dots, also another format issue, that's the actual mean temperature for that year. The dark line here is a 9-year moving average that's meant to smooth out some of the variability from year to year, give us some of these decadal type of trends. And what you can see is that at the end of the 19th century here, we had a little bit of a warming trend of about a degree Fahrenheit, a leveling during the 30s and 40s. That was followed by a slow cooling trend, again of about maybe a half a degree Fahrenheit that lasted until the late 70s, early 1980s. And then we've had about a 2 degree Fahrenheit increase in mean temperature since then. So overall, again, a degree and a half Fahrenheit warmer than we were in the past. It's also two other things to note about this. This is not symmetrical around the annual cycle. We've had relatively more warming in the cool season, in winter, also in spring and fall, and at night. Our nighttime temperatures are rising more quickly than the daytime temperatures. So our diurnal range, the difference between those two is shrinking, especially the nighttime temperatures, and especially at winter. There are portions of the northern part of the region, the UP, and westward over into northern Minnesota, Wisconsin, where mean nighttime temperatures and minimum temperatures in the winter have increased as much as 10 degrees Fahrenheit. That's a huge, huge change climatologically. It's not quite that here, but it's still one of the largest. There's some seasonality to that. The other thing to note here too, and you can sort of pick this out, and it's one I'm going to get to in just a couple minutes, but you could make an argument that at least from year to year, we see a little bit more variability around that long-term moving mean. And variability is a big deal, and it's something we know a little bit less, but you can make the argument here that our interannual variability may be increasing somewhat, at least for some variables. So now I'll get back to that. Winter temperatures, one is we have less ice for less time on the Great Lakes. This is collective ice cover, or average ice cover, taken from satellite. This one only starts in 1980-81. What you can generally see here is that ice cover in the lakes, at least in terms of the long-term mean, peaked back in the late 70s and early 1980s. And it's been declining ever since. But, and again, back to the issue of variability, everyone, you remember this year, probably not in a positive way. 2013-14 and 2014-15, the two most severe winters we've had here in Michigan, actually in over 100 years. You've got to go back to 1911, 1912 to see anything like that. Those years were just off the charts. Just this past year has been, it started mild in December. Cold, we had above normal ice coverage. This is the first estimate of that. It was also above normal in the year, the 2017-2018 year as well. And so even though the long-term trend is downward, one again would have to make the observation that there has been an increase in variability from one year to the next. That's not good. And I'm going to talk about the Great Lakes in just a second because it's linked with this particular piece. And another example of how all these trying to show you a number of different variables. These things are linked together. They're physically linked. It's part of our environment. So again, with milder temperatures in the winter, on average, we're tending to see less ice with time. There's a direct link between the two. Seasonality is changing. This one probably also you're aware of. This is a bit of a mess. It's a spaghetti graph. There are 3 series plot on this one. Again, back to 1895. And it's not quite up to date. But the issue is we have both. This is the change in the date of the last freezing temperatures of the spring season. That's in green. The date of the first fall freeze, or the first freezing temperatures in the fall, and that's in blue. And basically, this is the change in days as we move through time. The dark brown color here is the length of the so-called frost-free growing season between the last freeze of the spring and the first freeze of the fall. What you can see collectively is that since magically, the year 1980 shows up many, many times, since the early 1980s, the last freeze of the spring has tended to occur gradually earlier with time. The first freeze of the fall is occurring later, and what we've got in between, of course, is a longer frost-free growing season. And we've looked at this in detail in Michigan, and it's not symmetrical. More of it's occurred in the spring. There's a bigger change, but in many parts of western lower Michigan, we have added at least a week and a half of frost-free growing season that we didn't have just 30 or 40 years ago. It's a big change. There are major implications for this for perennial crops and natural vegetation. One of the things I do, my specialty is impacts with agriculture, and for our tree fruit industry, this is a huge, huge issue. Suffice to say, the seasons are changing as well. Arguably the largest change climatologically here in our region over the last several decades is precipitation and increases in precipitation. And I'm sure, especially this part of the state, there's no need to dwell on it. You've all seen evidence of that. But this is the same time frame as we saw for temperature, 1895 through the end of last year. Same format. And what you can see is that really since the 1930s, the Dust Bowl era, which was the benchmark driest decade on record across much of central North America, not just the Great Lakes. Ever since then, with a couple of periods here, late 50s, early 60s, and then again in the late 90s, we've generally been trending upwards with time. 10 to 15% more precipitation now. This is liquid plus melted, solid, frozen precipitation. Everything together in the rain gauge. That equates to about 3 or 4 inches on average. And to think, well, what does that mean in a real world situation? What's monthly average precipitation for the month of June here? 3.5 inches or so. What it means, at least on the surface, is that we have a whole extra months of water now that we did not have just a half a century ago. Huge implications for that as well. You can have too much of a good thing, and I'm going to talk more about that as well. But that's I think this is one of the most important or significant trends we're dealing with. How do you get more annual precip? Well, there's two things happen. One is we have more days with precip, more wet days. That's increasing. And we also have more average precip per event, especially on that high end of the distribution. That's the too much of a good thing. We're seeing more extreme events. Both of those are happening to make up for that difference. Changes in snowfall are a little bit more difficult. There's two changes. One is that for portions of the Great Lakes region to our south and southwest, where all the snowfall essentially is synoptic, low pressure systems, fronts, that type of thing, big lifting mechanisms, their average snowfall is decreasing with time. It's noticeable, it's measurable. You can see that this is 1961 to 1990 on the left. Here's the current normals period, 1981 to 2010, and what you can see again is that these lower amounts have shifted northward, especially in the Ohio Valley. So there, less snowfall. But at the same time, you've also got areas of our region, especially up north, where average snowfall is increasing with time. And then, of course, the question is, well, how can it happen? What's going on? And the answer is, again, where you are, it's lake effect, snowfall. So we've got both synoptic and lake effect contributions to this, but this increase here is due to snowfall, which begs the question, well, wait a minute, you said it's getting warmer, the winters are getting milder, there's in some cases there's more ice. Well, these are all linked together because as the lakes get warmer, and the water temperatures are increasing with time as well, especially Lake Superior, they're staying open longer. Remember, when ice covers a lake like it did, most of it certainly did in the northern parts of the region this past winter, it shuts off or dramatically decreases lake effect snowfall. So yes, we still have Arctic air masses that do migrate, and we saw ample evidence of that earlier this year, but the lake effect component is increasing. This is even more true in the lower lakes, over on Lake Erie in Ontario, but it's happening here in Michigan. So two different directions for snowfall. And you might ask the question, and we have to. The question is, why do we see so much precip? There's actually some very recent work done at the University of Iowa, the hydro group there, which is really interesting. And it basically said, well, if we want to understand climate here, we have to understand the weather, the shorter term pieces of the shorter term cycles within climate. And you go to the jet stream. We have to look at the jet stream and the behavior of that's what controls, that's the overwhelming control of our weather and certainly of our climate over time. And what you find is that when we have these very wet periods in our record, many of them tend to be associated with this particular upper air pattern. This was taken from February this year on average, and that is, if you don't mind some of the meteorology geeks speak here, troughing out over the western part of North America, ridging over the east, southwesterly flow aloft here, and this does a couple things. One is this kind of pattern is conducive for the formation of big low pressure systems moving from the southern Great Plains northeastward into the Great Lakes. Think about our spring. That's one after another, after another series of those. The other thing that's just as important, maybe more important, is with that upper air pattern, at the low levels, we tend to have southerly winds off of the Gulf of Mexico. Where does our precip come from? Well, it's water vapor. The water vapor's got to come from somewhere. Some of it comes from the landscape, from plants, from transpiration. But the overwhelming majority of it comes from our nearest ocean, at least for us, and that's the Gulf of Mexico. That's the source. We get some from the Pacific, some from the Atlantic, but most of it is from the Gulf. And in this pattern here, you've got flow all the way from the Gulf of Mexico upward north into, and for most of the Midwest, that's true. So this pattern is conducive for that transport of water vapor up, and it just happens more frequently at times. And this, again, the research at Iowa basically said that the majority of this increase in precip, which we've seen across much of the Midwest and the eastern U.S. for that matter as well over the last few decades, is associated with an increase in frequency of this pattern. That's a big deal. That's a big deal because it's actually getting to the cause and effect of this. Now, why that pattern is so persistent, that's the next huge obstacle. Some of it is sea surface temperature patterns, there's a number of things, but that's at least the science is getting it. But which brings us to the Great Lakes. This is actually the whole series going back to, I believe, the mid-teens, 1915, with a Corps of Engineers on the different Great Lakes. And the last several years here have been very, very unusual. We went from record or near record low lake levels at the end of 2013. I think everybody remembers that, and there were vegetation and so forth growing out in what used to be the lake. That was followed by that horrible winter, terrible winter, cold winter. The lakes froze over and shut off evaporation. It was also much wetter than normal for the winter of 2013-14, and we had this dramatic reversal. Here's Lake Michigan, Huron right here. The largest increase, or the most rapid increase in our lake levels, at least in the 100-year or so series that we have. And they stayed there, they're still increasing. And there's a fairly significant chance. We've already broken records for the month of May. Most of the records in the Great Lakes are set later on in the year, but there's a good chance that we may break the all-time records here this year because we're at the very, very top. So again, we went from the bottom, the lowest, to the top. Variability. And that's the key issue. And the lake levels themselves are a reflection of the balance between the water coming into the system, of course it's precipitation, and that which leaves. And also there's runoff. Of course you've got runoff in the landscape and the drainage basin, which is related back to precip. But the loss of water is evaporation, and so it's a balance. There's a little bit with the engineers controlling the locks, but it's tiny. It's a fraction, tiny fraction compared to the climate part. So we're looking at these fluctuations, and remember that issue of variability, which I just can't, I think, overemphasize enough. Which brings us to this idea: why do we care about variability in these changes? And that is, we know that humans, over a long period of time, have been able to adapt or cope with steady changes in climate. There's a number of examples of that. And people sometimes are very clever, which goes back to Mayor Hartwell's comments, I think. We have a great deal of capability to address these issues, and even people thousands of years ago did the same thing. If the changes are stable and so forth, we have a lot better chances of success. However, if we have changes in variability, the problem is that those adjustments, those coping and adaptive strategies become much more complicated, much more difficult. Impacts of extreme events are one of those, and even though they're rare or uncommon in terms of frequency, they're associated with a large fraction of the impacts that we all care about. You think about tropical cyclones, hurricanes, droughts. Droughts are a big one in human history, unquestionably. These are the big ticket items, the ones that really matter. And again, they are associated with these long-term changes. There is evidence, and I'd like to start by looking at the distributions of record high temperatures and low temperatures by decade. This is a fairly interesting diagram from the U.S. National Assessment, Climate Change Assessment here. Back to the 50s and up to the first decade of this century, and this is the basic fraction of record high and low daily temperatures in the United States over the last several decades. And what you can see here is a gradual shift. Remember the temperature trend that we looked at for Michigan, but what you can see is that the proportion of record high temperatures, daily high temperatures, has definitely jumped over to the maximum side. We're seeing a shift of the entire distribution for temperature. We are, in some ways, for precipitation as well, but especially for temperature. That's what we were going to talk about. I don't want to do a statistics lesson here that's going to bore people, but it is very, very important to note, especially for those events out in the tails, the extremes. And that's why I bring those up here. There's a lot of empirical evidence to suggest that we're seeing a shift of the distribution upward as things warm up. Here's an example from Michigan. This is looking at mean January temperatures, and this is Traverse City. And we're looking at two different 30-year periods. 30 years is the period we use for our climate normals. 1951 through 1980, that's the dark color here, or darker blue, and then 1981 to 2010, that's our current normals period. That's the lighter blue, and you can see the shift of the distribution that's taken place over the last half century. Interesting to note that our lower end of the distribution, we still have some really cold winters occurring, but they're less frequent than they were in the past. And at the same time, on the higher end here, the most recent period, the 81 to 2010, you can see we've shifted over the frequency of these warm Januaries. And this is fairly typical. So this is real data, real observation, and shows statistically how things are changing. This is an interesting one. If we look at the absolute coldest temperature each year, the extreme minimum temperatures, again for Traverse City, same exercise. In this case, we actually have a phase shift. So this one right here, we're changing both the shift of the median, the middle point of the distribution, and the variability. Both of those are changing in time. This one is more of a phase shift. We're just picking up the distribution and we're moving it upwards. In this case, almost 7 degrees Fahrenheit. So the extreme minimum temperature each year on average is at least, well, 6 or 7 degrees warmer now on average than it was 30 or 40 years ago. That's a tangible change. And again, in terms of number of impacts for that, if you look at the change in law, these are multiple days, three days plus. Heat waves, not much to say, talk about that yet. There's not much of a change. 1930s were the benchmark, again, hot and dry. They probably will be for a long time. Same with cold waves on the other end of the distribution. Not much of a real temporal change at all. But here's a change that is real. And this, if you look at the USDA Plant Zone Hardiness Index, this is the original map based on the 1951 and 1980 data on the left. Here's the current map, which is updated. This is an index based completely on that variable I showed you, the extreme minimum temperature. And for most of the US, it's a little difficult to make up here. We've gained at least one whole zone in terms of plant hardiness. So towards the warming, and that's one manifestation of that change that I just showed you, basically looking at the whole US. Heavy precip, I talked about this just a little bit. I have a grad student right now working on a project looking at heavy precipitation events. And as the precipitation increases, again, some of that, a significant fraction of it is these heavy events. So these large reddish circles here, brown circles here, are all increases looking at the top 3% of the distribution, really, really heavy events, so 3+ inches or so events that occur on a given, these are daily amounts. And it's happening all across the region, both the upper Midwest and certainly across the Northeast as well. If you're wondering how much has this changed over time, this is an example for Lansing. Let's look at this recurrence interval is the expected time that between, well, of this magnitude. For Lansing, 4.8 inches was considered to be 1 in a 100-year event on average, frequency of that. And you can see that was updated in the 90s. It went up to 5.25. The current one now from NOAA Atlas 14 is up to 5.5 inches. So again, about 10 to 15% we've added on that end of that distribution. We've had a number of extreme events in the last several years. One of them was February of last year, of 2018, a big flooding event. This is Houghton on Father's Day, June 17th of 2018. 7 inches of rain fell. But this is directly looking at this, and if we look at one single climate weather-related problem or challenge, for us, for Michigan, and for much of the Midwest, this is it. The heavy rain events and heavy flooding. We do have the only other one, well, one doesn't get as much publicity, but it's droughts. 1988 drought. If you look at economic impact, those are big, but they are dwarfed. All of our biggest events in Michigan are heavy rain flood events. This is arguably our biggest challenge. We were lucky here in Michigan. We don't have to deal with landfalling Category 5 hurricanes. We see tornadoes once in a while, but they're much less frequent than they are to parts or places west and south of us. We have some blizzards, but collectively, we're pretty fortunate. But this is, again, if we want to look at a threat, these heavy rain events are it, and they're increasing, both in terms of the magnitude and in terms of frequency. One positive thing, as it gets wetter, the occurrence of drought on average is decreasing. And that's what this index is, a little difficult. The negative values here are droughts. You can see long-term trends are upward. And it's as we have more water, so that's a positive thing. Doesn't mean drought doesn't happen, it's just that it tends to be less frequent and less severe than it has been in the past. There's a lot of evidence for that. This is an interesting graphic here. This is looking at the number of $1 billion plus weather disasters in the United States by year, back to 1980, and there's an unquestionable increase in these. Now, first thing I'll tell you is these are adjusted for inflation. And here's the real curveball. If we look, what are most of these associated with? Well, flooding is in here, tropical cyclones / hurricanes, got winter storms, severe thunderstorms, tornadoes, etc. They're all in this mix. Why is this increasing? There's a concerning answer, and that is unavoidable. It's that we as humans have more stuff in the way. And that instead of becoming more resilient to these extreme events, these storms and so forth, it suggests the opposite is true. And I think that's a real red flag. And again, if you're in, the risk is changing with time, and it's not in a positive way. So let's look really quickly where we headed. I mentioned warmer and wetter. Well, there are no exceptions. All of the projections for the future suggest even more warming in the future, especially if we consider high emission scenarios where there's no effort made to try and either to reduce the emissions or reduce the amount of carbon and nitrogen in the atmosphere that's already there. There's a number of ways you can go about trying to alter this. But the business as usual has about a 4 degrees Celsius warming by the end of this century, so 7 degrees Fahrenheit, something like that. There is, though, importantly, if we were able to rein in the emissions and maybe begin, efficiency, there's a number of ways to do this. We're already committed to some warming based on what's happened since the end of the Industrial Revolution, but we would see a much, much weaker maximum, and also you can see leveling off already occurring. So it's a very, very different scenario, and it's why I would say you have to look at this. It is worthwhile. Yes, there's been warming, and there probably will be a little bit more, but it would be much less than what it is for these other scenarios where there's much less effort made to try and change things. For Michigan, it's even larger. Much of the high latitudes and the mid latitudes, there's relatively more warming. This is the same type of projection for the state of Michigan, and you can see somewhere between 4 to as much as 15 or 16 degrees Fahrenheit on average. That's extraordinary. We've seen nothing like that in our record, depending on the emission scenarios. So huge projected increases in temperature in the future. One way of looking at this, looking at analogs, some of you have probably seen this, it's oversimplified, but it still makes the point. If we consider current climates, and how far would you have to go to find 10-degree warmer climate? Well, you can see you'd have to go probably all the way down to the lower Mississippi Valley or even the Southern Great Plains. And I think we can all appreciate their climate obviously very, very different than it is here in the Great Lakes. That's a big change. It doesn't seem like that much, a few degrees, but it makes a huge difference in our environment. Precipitation-related changes, most of these projections, not all of them, the majority of these suggest, at least for the next few decades, more annual precipitation, but then a leveling off and then maybe a drop towards the end of the century. One of the rubs here, the one thing I wanted to talk about was we hear the statement, both more heavy rain events and more droughts. And a lot of people say, whoa, that doesn't make any sense. And of course, physically, there's only one way that can happen. And that is, yes, maybe we have more annual precipitation, but it falls on fewer days. It's the word that needs to be used, and it's I'm one-man campaigning for this, is erratic. Erratic is bad. There's almost, unless you sell irrigation equipment, nobody else benefits from more erratic precipitation. For both natural and human systems, it's a bad thing. And unfortunately, many of these projections, that's what they suggest, especially for the middle of the century onward into the latter part of the century. So I think that's a major take home. There's also some seasonality, even for the projections that say wetter climate, most of the precipitation occurs in the cold season and is rainfall versus frozen snow or snowfall. The summers are level, and of course the summers when we need the water for all of our systems. So there's some big red flags, quite a bit of research going on in that. Some of the earlier studies were really huge changes suggesting. The Catherine Hayhoe study here on the left, up to a meter drop in lake levels, and they got a whole lot of publicity about a decade ago. There have been a couple studies since then. I'll cut to the chase here, but the most recent, there's a really good mileage study done at the Great Lakes Environmental Research Lab. NOAA, with Drew Grunwald and Brent Lofgren, and what they have found is that it's a very challenging thing to do, but the changes that they see are relatively minor. Some minor decreases, some minor increases. That's where things are right now, and Brent, a good friend, he would be the first to tell you there's still a lot of uncertainty about this. One thing that they do say, that talk about that is also relevant, especially here in an area so close to one of the Great Lakes, there are big changes in temperature. And so there will be ecological changes in the lakes themselves, which we need to be concerned about, fish populations, etc. That is highly likely. The stratification, the timing of that definitely changes. The levels, again, there's still more work that needs to be done. And so, again, summarizing here, warmer and wetter, historically, especially over the last half century, it's what at least is projected for the next few decades. Collectively, the issue of variability is one that we know less about. And it's one that more research is needed because it's where a lot of the impacts are. Given the projected rates of these changes in our climate, which are far beyond what happens naturally from we know in the natural, so that's one difference between human-related climate change and that natural system. Our systems, our planet has to be dynamic. Looking at this, and to take science, take our best efforts to understand what's happening and educate. And we're doing a good job of that. We also have to think of our own, for old people like me, our peers. It's a multi-generational issue. We have to tell the story. Your role is absolutely, it's at the top of the list, mission critical. We have to continue to tell that story. And to, again, truth, we have to be true to ourselves, and we are responsible too for those who come after us.